Located west of the city of Kingston, Canada, on the north shore of Lake Ontario, the Lafarge Corporation operates one of the largest cement kilns in North America at its Bath plant. This 3,400 tons per day plant was built in the 1970s. After running for a quarter century, the 655-foot-long kiln experienced frequent refractory failures in the burning and upper transition zones. This led to reduced operability and unplanned shutdowns. In fact, more than 130 feet of the kiln at the discharge end had become severely deformed and was in need of replacement. Lafarge chose Krupp Policius Corporation of Atlanta, Georgia as its engineering and equipment supplier for this extremely challenging turnkey repair project. Krupp Policius chose to partner with PMI, the rigging and millwrighting division of the Process Group of Canada, to undertake the equipment delivery and mechanical erection of the replacement kiln components. PMI Engineering and Construction Management were assigned the task of studying the technical requirements of the repair in order to analyze the logistics of various construction techniques and to design a solution to the constraints of the project. Only 36 days were allowed to execute the kiln section replacement during a January planned plant shutdown. Any longer would have a serious impact on Lafarge production and sales for the year 2000. The Canadian winter also imposed potential adverse conditions and presented a significant risk to completing the job on time. The PMI solution to the time and weather constraints was to adopt a one-piece kiln section out and in strategy, which required the following logistics and rigging methods. 1. In advance of the plant shutdown, PMI would receive and pre-assemble the complete replacement kiln section on the ground adjacent to the operating kiln. 2. A lifting tower system would be erected between piers number 1 and 2, ready to accept the damaged kiln section on shutdown day. The 450-ton, 130-foot-long damaged kiln section would be isolated, lifted, rolled away, and lowered to the ground for demolition and removal from the site. 3. The 650-ton, 130-foot-long replacement kiln section would be skidded downstream from its assembly location to the lifting tower system, where it would be raised, traveled to the piers, lowered to final position, and connected to the existing kiln. 4. In between the kiln section removal and installation, the pier number 2 roller station was to be removed, the pier rebuilt, and the new roller station installed. This innovative approach won the approval of Lafarge, as it allowed them to run the kiln until the very last moment, and it presented a plan and schedule that could be accomplished within the stringent time constraints. The weights and diameters of the replacement kiln components were of such enormous proportions that the only practical method of shipment was by water. The kiln components were shipped on an ocean-going vessel from Antwerp, Belgium, to the port of Montreal, where PMI received them. The concerns about weather conditions became well-founded when the ocean vessel encountered severe weather in the North Atlantic. This delayed its December arrival at Montreal and threatened the window of opportunity to use the St. Lawrence Seaway before winter shutdown. The final delivery required the transfer of the new 19-foot diameter shell, the 24-foot diameter tires, and the rollers to a barge for shipping up the St. Lawrence Seaway. By now, the Seaway Authority had removed all the navigation buoys in preparation for closure of the shipping season, thus limiting traffic to daylight movement only. After convincing the Coast Guard that the PMI tugboat had sufficient GPS equipment to safely navigate around the clock, 1,000 tons of cargo and equipment finally left the port of Montreal the week before Christmas. The tug-driven barge was the last vessel allowed by the Seaway Authority to pass through the locks before the 1999 closure deadline. The barge sailed through the icy St. Lawrence River and was secured in Kingston Harbor on Christmas Eve. After several aborted attempts, due to high winds coming down Lake Ontario, the barge traveled the last 20 miles to the Lafarge jetty, arriving on New Year's Day. PMI selected a low-draft, roll-off barge to be fitted with stabilizer outriggers and a 30-foot removable exit ramp to overcome an unfavorable shoreline. The benefits of the roll-off strategy were quickly realized. Tractor units were hitched to the transporters, and the hydraulic feature to raise and lower their decks proved to be advantageous as the sequential unloading of the barge progressed. As transporters returned empty, they could be redeployed to slide underneath the cargo and then raise the deck to carry the next component to the site. As the components arrived in the laydown area, the self-unloading feature of the transporters was used to place each piece in a predetermined strategic location so that it was only one crane set up and lift away from its final position in the assembly area. To complete a kiln assembly for a one-piece lift requires detailed sequence and management planning. The footprint of the assembly area was located to complement the chosen rigging method for the kiln removal and replacement plan. Cranes were used to slide the enormous splined tires, weighing 100 and 157 tons each, onto two of the heavier kiln shell sections. The whole process resulted in the assembly taking place on pre-positioned power turn rolls, followed by the alignment and weld-out of the tire pad hardware, requiring 2 tons of electrode applied by the shielded metal arc welding process. A large weather shelter was erected around the assembly to help contain preheat temperatures and to protect it from the elements throughout the welding process. Cranes were again used to place the remaining 3 intermediate kiln shell sections. Once the one-piece kiln was assembled to within acceptable dimension tolerances, the shell joint welding was allowed to proceed. The power turn rolls located at the tire support points provided controlled turning of the complete assembly to less than 25 inches per minute, crucial for a quality, automated, submerged arc welding process. Upon completion, inside spider bracing was installed at calculated lift points, and all the welds received a series of non-destructive examination and testing. While all this was happening, the existing kiln was still producing cement clinker, and plant operation had not been interrupted. Several concurrent activities were scheduled, timed to the completion of the new kiln shell pre-assembly. The canopy over the damaged kiln section and a portion of the burner building wall was removed to provide access for rigging. The existing kiln upstream of the cut line between piers number 2 and 3 required a 400-ton capacity 4-point hydraulic gantry system for the unsupported shell after the cut, and also required a spider inside the shell at the saddle support point to maintain the kiln shape. An 800-ton capacity lifting tower system was supplied by Atlas Industrial Contractors and modified to satisfy the PMI engineered rigging plan. This system required 2 8-foot wide by 105-foot long fiber-reinforced concrete foundations to be constructed below and perpendicular to the kiln in order to provide a sound and level runway for tower travel on twin 15-inch 400-ton capacity gantry tracks. The lifting tower was equipped with twin sets of W30 headers that supported 4 PSC L180 strand jacks designed to lift the one-piece kiln assembly via 2 70-degree massive saddles. These saddles were supported on twin sets of W36 lifting beams, where 4 sets of 12 3/4-inch strand cables were dead-ended. These saddles also required shimming to accommodate the 2.6-degree slope of the kiln. The kiln shell was fitted with inside spider bracing at saddle lift points, and the removal process started with the cutting of the kiln shell 1 foot outside the burner building wall and 30 feet upstream of pier number 2. The fully braced lifting tower and strand jack system then picked the 450-ton, 130-foot-long damaged kiln shell out of the rollers and was slowly propelled away by hydraulic jacks connected between the tower leg base rollers and the twin-track runway system. Once the 35-foot horizontal travel was achieved to clear the piers, external A-frame outriggers were installed on the tower legs to maintain stability, and the tower cross bracing was sequentially removed as the kiln was lowered to the ground for further demolition and removal from site. The remaining outlet section inside the burner building and supported by the 40-ton gantry was then removed using a 250-ton Krupp mobile crane. Because the new spline tire was significantly larger than the old tire, concrete pier number 2 had to be cut down by approximately 4 feet and recapped for the geometry of the new roller station. Upon completion of the pier number 2 rebuild, the base frame and pre-assembled roller components, weighing 106 tons apiece, were hoisted using a 400-ton Liebherr mobile crane rigged with a superlift attachment and installed subject to critical alignment tolerances. The final demanding exercise was the erection of the replacement kiln assembly, which began with the placement of a new kiln outlet section inside the burner building using a 250-ton Krupp mobile crane. Again, the 40-ton gantry provided temporary support, and the spider bracing kept the shell round throughout the handling and assembly process. The PMI 400-ton per pad capacity skidder track was already under the kiln tire turning fixtures. The hydraulic skidder system was then employed in a leapfrog manner over leveled crane mats to move the 650-ton kiln assembly parallel to the existing kiln shell, approximately 150 feet, to achieve proper placement under the lifting tower. There, the 130-foot-long kiln assembly was transferred to the lifting tower saddles and slowly raised by the 800-ton capacity strand jack system to a height of 50 feet, while tower cross bracing was sequentially installed below the load to stabilize the lifting tower system. The A-frame outriggers were removed from the lifting tower, and the tower leg propulsion jacks were again used to travel the assembly 35 feet along the track runway system, back to the pier and roller station location. To facilitate a fit-up of the aerial kiln joint upstream of pier number 2, the sloping kiln assembly was temporarily set down on the rollers and the saddles were repositioned before the final lift and translation of the kiln to a home position. The outlet section in the burner building was then fit up to the discharge end of the kiln assembly using the 40-ton rolling gantry. After final alignment was achieved at both seams, the aerial joints were welded by the specified shielded metal arc welding process. All welds passed non-destructive examination and testing, and a quality milestone was accomplished. The tires were finalized with fixation devices, the inside shell alignment hardware and spider bracing was removed, and the kiln was turned over to Lafarge 2 days ahead of schedule. This project was a partnering success for the Lafarge Corporation, Krupp Policius, and PMI in a number of ways. 1. 885 tons of replacement kiln components were manufactured and safely delivered from Europe to Canada under adverse marine conditions. 2. A one-piece kiln removal and replacement strategy was innovative and presented the only option to satisfy the client's plant shutdown time constraints. 3. Kiln pre-assembly handling methods and welding procedures were engineered to satisfy submerged arc welding process requirements in the field. 4. All welding operations were performed at controlled preheat temperatures under weather protection enclosures, and no weld failures were detected by NDE testing. 5. Hydraulic skidder, crane, hydraulic gantry and tower strand jack lifts were fully engineered and certified prior to execution. 6. Work was performed during Canadian winter conditions involving over 1,000 man-hours of engineering and planning and over 18,000 direct labor man-hours of effort, and was completed with no accidents or incidents. 7. Critical path planning and scheduling techniques were employed to achieve a 2-day improvement in the client's 36-day contract requirement. 8. The project was completed under budget, meeting quality guarantees and client satisfaction.